morning. Welcome to TMMS Productions. Today we are going to prove the Pythagoras Theorem. Pythagoras Theorem is one of the most fundamental rules of geometry. Similar rules were in practice in ancient Babylonia and also in India. There are about 350 plus proofs for the Pythagoras Theorem. Here we are going to just look at two proofs. Let us first see the statement of the theorem. The statement of the theorem says, in a right-angled triangle, the square on the hypotenuse is equal to the sum of the squares of the other two sides. And so, let us see if we can look at the diagrammatic proof of this. Here you can see that I have a triangle ABC with BC as X, AB as Y and AC as Z. And so, according to the Pythagoras theorem, it becomes AC square, which is the square on the hypotenuse of the right triangle. Now, in a right triangle, it is necessary that one angle is 90 degrees and the other two angles, they will be complementary angles. They will be adding up to 90 degrees. And now, opposite to this 90 degrees is AC. So, AC becomes the hypotenuse. And so, the square on the hypotenuse, which means it will be Z square, which is written here, is equal to the sum of the squares of the other two sides, which is this square plus this square, which is what I have written. Now let us look at it from a diagrammatic representation. Let us take a square, and the square, each side is equal, you know that, and we are going to divide this side into two parts. One will be X and the other one will be Y. And I have taken the same measures as this X here and this Y here. And so we have converted this side into this much of Y and this much of X, and then again Y and then this X and this Y and then this is X. So you will see that each side is X plus Y, X plus Y, X plus Y, X plus Y. Now let us look at our proof. Now I have cut out a triangle, black in color, which is having exactly the same dimensions as our triangle ABC. Now you can see that I have cut out similar triangles and I have kept them in such a way that the Y of the triangle coincides with this Y of the square. X of this triangle, that is the length of BC, coincides with this X of the square, and so this is giving you X plus Y, and now we have kept them like so, and you will see that here we have got a square again inside, and each one of these sides, this is Z, this is Z, this also is Z of this triangle, and for this triangle this is also Z. And so you will see that this square, the area is going to be Z square. So now we are going to rearrange this by moving the triangles like so. So now, after moving these triangles in such a way that the whole area will look like the four triangles plus this small square and this big square. And so we now understood that our earlier square, the big square, which had each side equal to X plus Y, was actually 1, 2, 3, 4 triangles plus the big square, which was Z square. And now the same square is now these four triangles plus one small square here and a slightly bigger square here. What does that mean? That the area of this big square, which is yellow square, is actually equal to this small square plus this small square. Now let us see how we can depict it in color. It will look like this particular square which I have shaded green, and this square over here which is again shaded in green, and here you will see that each side of this small square is x unit, so this becomes x square, and for this each side is equal to y, so this is y, this is y, this side from here to here is y, and so this square is y square. And so you will see that the entire square, which has the area x plus y whole square, each side being x plus y, this also x plus y, this also x plus y, this also x plus y. So it is x plus y whole squared is actually made up of this yellow square, which is z square, and plus 4 triangles like so, the area of 4 triangles. But now when we rearranged the triangles, we had the 2 triangles sitting here and 2 triangles sitting here. So it was now this x squared, which I have written here, and this y squared, which is written here, plus the 4 triangles which sat over here, the 2 here and 2 here. So the entire area is equal to z square plus 4 triangles is equal to x squared plus y squared plus 4 triangles. And the area of 4 triangles will get cancelled from each side, and that will give us z square is equal to x squared plus y squared, and that is our statement of Pythagoras theorem. And so if you look at the triangle, we have z square, which is the square on the hypotenuse, is equal to x squared plus y squared, means the squares on the other 2 sides, when you add them up, they will add up to the square on the hypotenuse. So that is our first proof. So we start by drawing the diagram PQR, and we are going to use similarity for this. So whenever we have a proof, we should write what is given. And in a triangle PQR, angle PQR is 90 degrees. And to prove that the square on the hypotenuse is the side opposite the 90 degrees angle. So PR square is equal to PQ square plus QR square, that is the sum of the square on the other 2 sides. So we have to construct this QS perpendicular to PR, and we write construction, draw QS perpendicular to PR. Now in order to use the similarity for proving the Pythagoras theorem, we need to look at the 3 triangles which are here. One is PSQ, the other one is QSR, and the other one is PQR. And we have to prove PQ square plus QR square is equal to PR square. So we need to take 2 triangles which will give us PQ first, and so we will be using this triangle first. And each one of these triangles are similar because they will have the same measures of corresponding angles. So we have this 90, this 90, this 90. If I call this as x, this becomes 90 degrees minus x, and this angle becomes 90 degrees minus x, and this angle becomes x. So you will see in these 3 triangles, we'll have 90 degrees, x, and 90 minus x, and here as well 90 degrees x and 90 minus x, and of course the big triangle will have 90 and then x and 90 minus x. Now in order to start with PQ square, we will take two triangles which will have PQ as the common side, and that will be PQS and PQR, but when we write it in correspondence. So I have written the proof and the two columns for statements and reasons, and then I write in correspondence statement number 1, which is in triangle PSQ, I take the common angle for the two triangles, then 90 and then the third one. For the big triangle also I'll take common and then 90, that means PQR. So in triangle PSQ and triangle PQR, the first angle I'll take is 90 degrees. So in this triangle 90 is here, so I'll take PSQ, that is what I've written, and so PSQ corresponds to PQR. So PQR, and that is equal to 90 degrees. The reason would be given and construction. Statement number 2, we will talk about the common angle. Now common angle for the small triangle will be SPQ. I've taken 90, then common, then this. So for the big triangle again I'll take 90, then common and this. So PSQ is equal to angle PQPR. SPQ equal to angle PQR, and that's equal to x. You can see x degrees, and that's the common angle. Now once you have this, the third statement will make the two triangles similar. So for similarity, we'll take at the letter in the center SP and the third one Q. So we'll write triangle SPQ similar to, here again the center letter Q, P and R is the third one. So triangle QPR. So we have written the two triangles are similar, and we say from statement 1, 2 and AA test for similarity. Now once you get this, you have to take their corresponding sides, the ratio of it. So SP upon QP is equal to PQ upon PR is equal to SQ upon QR, and that will be from statement 3, and corresponding sides of similar triangles are in proportion. Now we are interested in PQ square. So PQ square means I will have to take the two ratios with PQ, this QP and this PQ. So I have taken the first ratio and the second ratio, and I have written them down as our statement number 5. And now SP upon QP is equal to PQ upon PR. Cross multiply. What do you get? PQ square. PQ square is equal to what? SP into PR. And that is from statement 5 we have derived. Now we have to come to QR square. Now QR square means I will have to take the two triangles. So it will be now this triangle and the big triangle. They have side QR common. And so let us write it the same way as we wrote statement number 7. So statement 7 says in triangle RSQ, let's write it common angle, then 90, then the third angle. So RSQ and triangle, the big triangle, again we'll start with the that is R, then 90, that is Q. So RQP, we write it in correspondence, and then we'll write the first angle equal to 90 degrees. Now which one is 90 here? This one. So that is RSQ, and for the big triangle it will be RQP, not PQR, because you have to start with the corresponding angle. So R corresponds to R for this triangle as well as the big triangle. So we'll have RSQ equal to RQP, which is what I have written, equal to 90 degrees. And then I have SRQ, the common angle, that is this one. SRQ is SRQ. And then for the big triangle, we will talk about the QRP. So we have SRQ equal to QRP, which is 90 degrees, minus x, which is the common angle. And therefore, the ninth statement will be, therefore, the two triangles are similar. So we'll write the center letter SR, then Q. So SRQ, and here center letter QR, then P is missing, so P. So SRQ triangle is similar to QRP, and that will be from these two statements, and A8 is for similarity. And once we have done this, we write the corresponding sides in their ratio. So SR upon QR is equal to RQ upon RP is equal to SQ upon QP. Can you see that? And so we will write from statement 9, and corresponding sides of similar triangles are in proportion. Then we move to the next one, which is we have to get QR square. So QR square is going to be, can you see the sides across here, QR and RQ? So we write this ratio down, and then we will cross multiply. So you'll get here QR square is equal to SR multiplied by RP. Now for statement number 13, we have to take this PQ square equal to SP into PR. So we'll write PQ square, which is this, plus QR square, which is this. So I'll write PQ square plus QR square. And for PQ square, I'll write SP into PR. Plus for QR square, I'll write SR into RP. And this will be from statement number 6 and 12. Now let us see what happens. SP into PR and SR into RP, both of them have this PR and RP is common. So I'll take out RP common, and here I will write SP plus SR. Now let us look at our diagram. RP is here and SP is here. This is SP, and SR is from here to here. So SP plus SR, SP plus SR gives us RP. So we'll have RP multiplied by RP. And this is because of the diagram, and that gives you your RP square, which is PR square. So what did we prove? We proved therefore PQ square plus QR square is equal to PR square. Let us look. PQ square plus QR square is equal to PR square, which means the square on the hypotenuse is equal to the sum of the squares on the other two sides. And this is the proof of your Pythagoras theorem. So I hope you have understood how to prove Pythagoras theorem. Now in our next video, we'll see how to do some of the questions based on Pythagoras theorem. Thank you for watching.